The objective of this video is to define an analytic procedure to determine the initial design of an AC machine. And really, the goal of this video is that we're going to develop a set of processes or a procedure that we can use to determine everything about a machine that we want to design. And this is going to be analytic. So when I say analytic up here, what I mean is that we are not going to rely on finite element analysis or any kind of numeric technique. This is strictly going to be a pen and paper approach. And as such, it's going to have inaccuracies. What you'll see at the end of this video is that I'm going to emphasize that we have to take this initial design and bring it over to a more detailed analysis tool, whether that's a magnetic equivalent circuit or an FEA tool, or this initial design could in fact be the template design that we use for an optimization procedure. So again, the goal of this is that we're going to take a design specification, we're going to take some kind of application requirement and invert that to figure out everything about our motor. This is a very hard problem. Inverse problems are in general hard. Anytime you're trying to invert something, you have to think pretty hard about how you're going to do it. But especially in this space, this is a really hard problem. There are so many inputs that determine how your motor performs. You have so many variables you can adjust. You can adjust your tooth thickness, your tooth tip depth, your axial length of your motor, what kind of motor you're using, whether it's got a squirrel cage or a permanent magnet rotor. You have nearly infinite set of variables that you can tweak about your machine design, but you have very few output performance requirements. Maybe you're told you just need to make a 10 kilowatt motor and it's got to spin at 3600 RPM and it needs to be 96% efficient. Okay, well now you've got three criteria that determine whether or not your machine is a good design, and yet you've got maybe 20 different variables that you can tweak to determine what your machine actually looks like. So inherently, this is what's called an under-constrained problem. We have nearly infinite combinations of variables that determine what our motor design is, and nearly infinite combination of variables that can give us a suitable motor design. And so to determine a set of variables that works, that meets our application spec, is difficult. So I want you to view this in this lens, that we're approaching a very difficult problem where we inherently cannot be overly precise because there's no one exact solution. Instead, we need to use our engineering knowledge to come up with a reasonable solution. Okay, so first we said that we have a goal of determining everything about our motor given a design spec that is under-constrained. We need just a few outputs, but we've got a bajillion inputs. Second is that we're doing this in a process that is imprecise. We're making simplifying assumptions just so that we can even approach the problem. And the corollary to this is to note that this process is going to have to be revised based on your specific needs and application. Our goal here really is not to define one single procedure for dimensioning a machine, but rather to talk through the thought process and the intentions behind approaching a machine design. So this really is not a one-size-fits-all approach. You will need to modify this to meet your specific needs when you are designing a motor. And finally, this initial design that comes out of this process is something that needs to be studied further before it can become a final design because of all the simplifying assumptions we've made. So the goal here is to make a set of simplifying assumptions that reduces our design problem to something that we can actually tackle, and then come up with a candidate design. And then we take that candidate design and we study it with a detailed analysis tool, most likely an FEA tool, and we determine how it performs and if it meets what we expect, if it meets the performance requirements that we expected it to meet. If it does not, we need to go back to our procedure that we're laying out in this video and adjust the design, adjust the dimensions, figure out what went wrong in our procedure and correct it, and then do another detailed analysis. And if that worked, then we're happy, we're done. If it didn't work, we have to adjust some more. So you can see that this is an iterative process and it's not a precise process. So this video is now going to outline a set of steps that we can take to construct this initial design. And the very first step is that we need to determine our design specification. And our design specification consists of many aspects. This is a specification you might receive from a customer if you are designing a motor as a product, or it's something that you might have in mind for a given application. So maybe your application requires a certain rated power or a certain speed, and it's immediately apparent that that part of the specification is completely defined. Other times, you're going to have to make a series of decisions. So when you're designing a motor, oftentimes an application is not going to tell you what materials you should be using for your stator laminations. You just have to make a decision at that point and move forward. When you come back and you iterate on your design, maybe you decide that your choice of M19 steel is just not going to cut it and you need to use an ultra thin gauge steel instead. Or maybe your choice of air cooling is not going to cut it. So we can view the design specification in all these categories that I've outlined here. The machine type, we need to decide what type of technology we're going to develop. Will it have permanent magnets? Will it have a squirrel cage rotor? Is it going to have a wound field rotor? Is it going to be a synchronous reluctance motor or a switched reluctance motor? So we first have to determine the type of machine that we're designing. And then we need to determine what I've labeled as user interface parameters. And those are the ratings of the machine, the power, the speed, the frequency or the number of poles we want our machine to have, what the voltage rating of the machine should be, how many phases it should have. And we need to determine, of course, what materials we're going to use, how we're going to cool it. Is it air cooled? Is it going to be direct cooled with a liquid, with a water sleeve perhaps on the stator? And you can imagine that there are other things that might come up that are unique to your specific application. Maybe there's a certain form factor you have to obtain. Maybe your application is only going to work if you have a stator diameter of exactly 200 millimeters. It can't be more, it can't be less. Well, this is the time to note that down and see how it influences your design process. Your second step is to determine the main dimensions of the machine. And to do this, we use our sizing equation that we've spent so much time developing. That sizing equation was that our torque on our rotor is going to be equal to 2 times the volume of our rotor times our average shear stress. And remember, this sizing equation incorporates key independent decisions in our design process. So we can express that shear stress as being our magnetic loading times our electric loading, and then times the sine of phi, which is related to the power factor of our machine. So your textbook gives you examples of achievable values of B delta and A hat. And this is the point in the design process where you have to pick what you are going to design for. We've talked about how you choose the sine of phi based on the type of motor. So this is going to be about 0.8 for an induction motor because you need to provide magnetizing current to magnetize the machine through your stator winding. For a synchronous motor, the sine of phi is typically going to be about 1. So we had these decisions about our electric and magnetic conditions. We also have to make decisions about the mechanical design of the rotor. And so VR is the volume of our rotor, which is of course equal to pi r squared times L, where r is our air gap radius, and L is the axial length of our rotor. And we make these decisions based off of, well, the mechanical integrity of the rotor, how it is able to withstand centrifugal loading, and so that ends up being a constraint on the surface speed of the rotor. So we can say that omega r is typically less than 150 to 200 meters per second. So that's going to set an upper bound for what the radius of our rotor can be. And then our axial length is going to be limited by the critical speeds. If you are engaged in a design where you need to think carefully about these parameters, that is a design that might be pushing the upper bounds on your structural strength or might be approaching critical speeds, I encourage you to consult a textbook or a reference material on the mechanical design of the rotor. Your textbook provides you some material in section 7.1.2. So the output of this step are the following parameters: your magnetic loading, your electric loading, the radius of your rotor, and the axial length of your machine. Step 3 is to determine your air gap length. And this, again, is something that you have to use your engineering judgment to decide. There's a trade-off here. Lower values of air gap length will tend to require less magnetizing current or less permanent magnet material, while larger values of your air gap length will tend to reduce the rotor and stator surface losses because it has a smoothing effect on the harmonic content of your air gap fields. It's hard to go below 0.2 millimeters for mechanical reasons. It's hard to keep your rotor sufficiently centered. And this lower bound of air gap lengths is typically what's used in induction motors, where the magnetizing current is a critical decision. If you increase your air gap substantially above this, your induction motor requires a very large magnetizing current. For permanent magnet motors or synchronous motors, an air gap length of 1 millimeter or more is typical. The air gap length also is somewhat a function of the power rating of your machine. For really large machines, for large diameter, large power machines, you typically need a larger air gap. And that's for mechanical reasons again. It becomes more difficult to keep your rotor perfectly centered to meet the tolerances of a very small air gap. So this is something that you have to decide based on your engineering judgment. At this point in the design process, you just have to make a decision. What are you going to use for your air gap length? Your fourth step is designing your winding. We've talked a lot about this in our winding design unit, but basically at this point you need to make a decision on the number of slots, the number of layers you're going to have, your coil pitch, or in other words your winding layout, and then you can do some calculations to determine what your phase current rating should be and how many turns you should have in each coil. So you're going to determine your number of slots and your number of layers, and you're going to do this to get winding factors that you prefer. We've talked previously about the importance of winding factors at different harmonics. So if you have a very high winding factor for your fundamental, you'll need fewer ampere turns to produce the same amount of electric loading. Whereas if your winding factor is low for your fundamental harmonic, then you need more ampere turns to produce the required electric loading. And more ampere turns means more copper losses, which decreases the efficiency of your machine. It also means more slot space must be allocated to hold the coils, which decreases your torque density. So in general, you want to have a high fundamental winding factor. However, this must be balanced against the winding factor harmonics. For higher harmonic values, you want to have low winding factor, and this is to decrease the harmonic content in your air gap. And reducing the harmonic content of the fields in your air gap will also reduce torque ripple and losses. This is especially important for permanent magnet machines, which might be prone to high losses on the surface of the permanent magnets. So you determine your number of slots, you determine the number of winding layers, and then you lay out your winding to get the best winding factors that you can. And now it's time to determine how many ampere turns you need within a slot. And so what you do is you solve our equation for electric loading. So you solve this equation where A hat is the electric loading that we previously picked up here. ZQ I hat is the total number of ampere turns in a slot. ZQ is the number of turns in a coil, and I hat is the current rating of that coil. R is the radius of our air gap. ZC is the number of coils that we have in a phase. And KW1 hat is our winding factor at the fundamental harmonic. We derived this expression a few weeks ago when we related winding factors to our current linkage and our electric loading. So this is an expression for the electric loading of a three-phase winding. And we solved that expression for ZQ I hat, so we know how many total ampere turns are required. And at this point, we need to make a choice. We need to pick what our acceptable current density is for a conductor. And you can do this by referring to table 6.3 in your book. So the current density in our conductor is related to the type of cooling that we use. And typically for air-cooled machines, a value of 3 to 5 amps RMS per millimeter squared is used. If you go higher than that, you risk overheating your coils and melting your insulation. So we have to pick this value of J. We can refer to table 6.3, which summarizes engineering best practices, but at the end of the day, we have to make a decision here. And next, we're going to pick a wire gauge to use. And we're going to make this decision based off of the skin effect in our coils, that is, based off of the frequency of our currents. If we have very low frequency currents, we can use really thick wires. If we have really high frequency currents, we need to have very thin wires so that we have proper conductor utilization. We talked about this in our loss video. So you're going to pick your value of J, how many amps RMS per millimeter squared you allow in a conductor, and then you're going to pick a wire gauge. Maybe this is AWG 18 or AWG 16 or AWG 22. And when you have these, we've made these two selections, you now have a conductor cross-section based on your wire gauge and the allowable number of amps per millimeter squared. And you can solve this to determine your coil terminal current rating, which then you can solve from this expression to determine how many turns you need within your coil. So this step has given us a value of I hat, it's given us a value of ZQ, and it's given us a winding layout so that we know what our winding factors are, we know how many slots we have, how many layers we have. In step 5, we determine how to meet the voltage requirements for our machine design. And our degree of freedom to tune this at this point is by placing conductors in parallel versus in series. So far in the course, we've only been considering all of our conductors to be in series, all of our turns to be in series, and all of our base windings to be in series. But that might not be compatible with the voltage that we require at the terminal of our motor. Maybe if we connected everything in series, we would end up with a terminal voltage of 1 kilovolt, while our design application requires us to keep a motor voltage rating beneath 500 volts or beneath 480 volts. And so our degree of freedom right now is to determine whether or not we need to place strands in hand or use parallel base winding. So strands in hand is a phrase that's used in the electric machines community to describe how when you're winding a coil, if you have multiple conductors that are in parallel. So you'd say, I've got 3 strands in hand, if when you're winding your coils, you hold 3 strands in one hand and wrap them around, and then at the ends, you short them together. So there are 3 conductors that are placed in parallel. So for example, suppose that you have 2 strands in hand in a coil that has 10 conductors. That coil would effectively have 5 turns in series, where each turn is composed of 2 strands that are connected in parallel. And we can use our expressions for the phase voltage that we derived in terms of winding factors to make this determination. And this expression came out of our star of slots video and our winding factor video, where we relate our voltage across a phase to the magnetic loading of our design, the air gap radius, the rotor speed, the axial length, the number of turns we have in a coil, and our winding factor, the total number of coils we have in a phase, multiplied by 2. So we know all of this information at this point. Our next step is to determine the width of a tooth. And to do this, I'm going to sketch a partial cross-section of a motor where I've labeled the dimensions on it that we've been working with in this class so far. So we've been considering this cross-section in our homework assignments, and this provides a fairly general parameterization for the geometry of the motor. I've labeled just a few key dimensions on here that's going to facilitate our discussion in this step and the next few steps. But basically our goal right now is to determine what the value of WST should be. That is, what is the thickness of these teeth? And notice that these teeth all have parallel edges. The edges are not going radially outwards, they're instead parallel to each other. That's an important property for these relations that we're about to be developing. And it's a typical way of manufacturing a motor. We like to have those parallel tooth edges. So the way that we do this is that we first need to determine what the maximum field we want to allow in a tooth. And your book again provides you some guidance on this. If you look at table 6.2, it will give you typical maximum field values for different points in your machine. That includes the tooth, the air gap, the back yoke, and so on. So based on that table, we can see that a typical value for a tooth might be something around 1.5 Tesla. So that's the maximum value that we ever want to see in a tooth. And that would be the field somewhere in this region. All of this region, we expect it to have a maximum field of 1.5 Tesla. Then the way that we determine what our tooth width should be is that we use conservation of flux properties. We realize that those teeth are just flux tubes. So what we're doing here is that we're recognizing that we're going to have a total flux within a tooth. We're going to have a total flux that's taking this flux tube path. And that flux is going to be this maximum flux, BT hat, times the cross-sectional area. The cross-sectional area is the width of the tooth times the length of our machine, the axial length of our machine. So that needs to be equal to something. And that needs to be equal to the total flux that we expect to cross the air gap over one tooth slot span. And so we can calculate that by integrating B delta over that surface area. So that area integral is going to be the integral of B delta of alpha times R d alpha, and over the bounds of one tooth slot span, which is alpha c. And if we're feeling lazy, we can just approximate this as being alpha c times R b delta hat. We can just assume that the field is a constant B delta hat over that region. Whether that's valid or not depends on how many slots you have in your machine and how much harmonic content you have in your field. If your air gap field is a constant value, if it's a square trapezoidal profile, then this might be pretty accurate. If it's a purely sinusoidal profile and you have very few slots, if it's a fractional slot concentrated winding, you may need to be careful about using this, and you might want to explicitly evaluate that integral. So if we take this lazy approach, we're then going to solve for WST, and we find the following expression. And you can remember that alpha c is just equal to 2 pi divided by our number of slots. So great. If we look at our progress so far, we have figured out what the radius of our rotor should be. We've determined our air gap length, and we have now determined our tooth width right here. Our next steps are going to take us through determining this radius, this length, and this length, and then finally this length. So we're coming up with a crude set of dimensions for our cross-section of our motor. Our next step is to determine the slot dimensions. That is to determine this height right here. And when we know that height, we already know this width, so we then know this full span of this slot. We know the full area of this slot. And the first step towards doing this is that we have to pick values for DSP and alpha ST. Remember, DSP is this length right here, and alpha ST is this span. And the way that you do this is you just need to make a decision using your engineering knowledge. So as you practice designing more motors, you'll gain more intuition for what these values should be. But typically, you want alpha ST to leave you with as small of an opening here as possible. This is called the slot opening in the center here. You want to have as small of a slot opening as possible, usually. And what do I mean by as small as possible? Well, you have to somehow install a winding in the stator. So the width of the slot opening needs to be at least large enough to get your conductors through so that they can reside in the back of the slot. And the more narrow you make this width, the more you reduce the harmonic content in your air gap fields, the more you reduce torque ripple and losses on the rotor surface. But you run up against how much space you need to get your conductors in the slot, as well as having a very short path for fringing fluxes to cross between your stator teeth. So the result of having too small of a slot opening is, one, you can't wind your machine, but two, you can end up with a large amount of leakage flux or a large leakage inductance in your equivalent circuit. So anyway, all that is to say that you need to make a decision here. You've got to pick a value for DSP and alpha ST. Next, you need to determine an estimated slot fill factor, and I'm labeling this as this variable KCU. So slot fill factor, what does that mean? If you look at your slot and you imagine that you've filled it up with a bunch of conductors, so you've placed a coil side within it, your conductors probably, in most cases, are going to be circular conductors, although you can use rectangular conductors. But suppose you've placed a bunch of conductors in here. You see that they are circles, and so they don't fully fit together. You've got all this space in between the conductors where you've got no copper within your slot. So you have this space for two reasons. One is that your circular conductors don't fit together very nicely, and the second is that you've got insulation on these conductors, which has some finite thickness, and that thickness of insulation is, well, it's insulation, it's not conductive. So the point is that this slot fill factor gives you an estimate for how much of your slot space you can fill with copper. So what we're driving to here is that we require a certain amount of slot space to hold all of the turns of our coil, and we need to figure out how much we have to derate our slot space by in order to have enough space to fit the whole coil into it. Since we can't use all the space, we need a correction factor on how much the slot space is actually able to be populated with copper. And the value of how much the slot space you can use, you can base it off of whether you're using a fractional slot concentrated winding, in which case you can typically fit more turns within the same amount of slot space. The reason for that is that if it's a fractional slot concentrated winding, you just have to wrap a coil around one tooth. It's much easier to get all your conductors bent and into the right orientation. And in some cases, if you've got teeth with no tooth tips on them, with no pull shoes on them, you can wind your coils on bobbins and then slide them onto the slot. If you're using distributed coils, you typically get a lower slot fill factor. Distributed coils means a winding with a coil pitch greater than one slot. And so using the slot fill factor, we can write this expression out. And this expression is telling us that the total usable area in our slot is equal to the slot fill factor times the physical slot area. And that is going to be equal to the number of turns that we have times our conductor's cross-sectional area. And then that will be multiplied by either 1 or 2. And so the reason that we multiply it by 1 or 2 is based on how many coil sides we have within a slot. So in a double layer winding, we have 2 coil sides within one slot. And if it's a single layer winding, we have only 1 coil side within the slot. So what we do in this step is that we evaluate this expression and we solve it for SU. We're trying to determine our required slot area. Next, we're going to relate our slot area back to our dimensions. And specifically what we're trying to do is come up with an expression for DST in terms of the required slot area. And the way that we do that is we can look at this cross-section up here, and we can say that our slot area, so that's this area in here, is going to be equal to the total area of a slot tooth span subtracted by the area that's populated by the tooth. So the area that's populated by the tooth is WST times DST. And we can do this, we can evaluate this by evaluating the surface integral over this entire span, that is 0 to alpha c, and then over this depth, which is DST. And so we're going to define an inner radius as being right here, Ri, and an outer radius, which is out here. So we're going to evaluate that integral, and we can immediately see that our inner radius is going to be equal to our air gap radius plus our air gap length divided by 2 plus DSP. And our outer radius is going to be equal to our inner radius plus DST. And so that's the integral that I've written down here. We're integrating from Ri up to Ro, and then over the angular span of 0 to alpha c, so over one slot tooth span. And we're subtracting from that the area that's occupied by the tooth steel. And so this is an estimate. Remember, this is all estimates. In this estimate, we're actually neglecting the available slot space that resides right here. And so this is a conservative estimate. If you expect to have very thick pole shoes, if you expect this DSP value to be larger, you might want to revise this expression to also include the area I've highlighted in orange here. And so finally, when we work on this expression, we get the following quadratic equation, which we're going to solve for DST. So at the outcome of this step, we now have determined a lot of variables in our machine cross-section. We've got variables for DSP, we got values for DSP, alpha ST. We've determined our slot area, which we then used to determine our tooth height, DST. So going back to our cross-section, we now have got our air gap length, or we've got our air gap radius. We've got all the dimensions of our tooth going up to here. And our next step is to determine our yoke thickness. And to help us to do this, I've drawn cross-section of a two-pole motor with a slotless stator and drawn the flux lines that we would expect to see in there if we did an FEA solve. The dimension that we're trying to figure out, again, is the thickness of our back iron, the thickness of our steel stator yoke. And we're going to do this again based on conservation of flux. And so what we notice is that we have a total amount of flux that crosses our air gap. So we can integrate all this flux out here, all this flux density out here to get the total flux that crosses our air gap. And we'll call this our magnetizing flux, Phi-m. Half of that flux has to cross through our stator yoke. So our stator yoke must carry half of our magnetizing flux. So half of the flux will take this path going this way, if we picture our magnetic equivalent circuit, and half of the flux will take a flux path going this way. And so conservation of flux, we can say that our stator yoke flux must be equal to 1/2 of our magnetizing flux. And just like we did for sizing our tooth width, we can plug in expressions for these fluxes. So our stator yoke flux is going to be equal to our field in the stator yoke times the axial length of the machine into the page times dsy. And then our magnetizing flux is going to be the integral of the flux crossing our air gap over one pole face. Okay, great. We now have dimensions for nearly our entire motor cross-section. The only thing that's missing is the thickness of our permanent magnets, or in the case of a squirrel cage rotor or a wound field rotor, our rotor winding design. And we've talked in this class about how to dimension our permanent magnets to get a certain air gap flux density, to get our no-load flux density, or our magnetic loading. We've also talked about how to dimension the field winding. We've not talked much about the squirrel cage, but this is the point at which you design your squirrel cage as well. And a second thing to add to this is that you presumably will also have to dimension your rotor yoke as well. So we have our rotor contain a lamination that has a certain thickness here, and then this region right here would be the shaft of our motor. So we'd have a shaft coming through this lamination. So in summary, this is a lamination, and then this is where our shaft resides. And so we need to make sure that we have enough thickness of this yoke right here to carry any time-varying field. The only remark I want to add to all of this is that when we dimension our magnetizing winding, or our magnets, we are quite tied to our air gap length. And that's fine. In a previous step, we determined what our air gap length should be. That was up here as step 3, we determined our air gap length. So we know that, but actually the effective air gap that our winding sees, or our permanent magnets see, is going to be a larger air gap. And that is because of the fringing fluxes that arise due to the slots of our stator. We talked about this a little bit at the very beginning of the course, how when you have an air gap in a magnetic path, you start to have to modify the cross-sectional area, or the effective air gap length, due to fringing fields. And we can understand this from the following drawing. And what you see is that in this region right here, between our slots, our flux has to take a longer path. And classically, how this is accounted for is we define something called a Carter coefficient, which modifies our air gap length. And so we can define an effective air gap length, delta E, which is equal to this Carter coefficient times our actual physical air gap length. And you can make calculations for the Carter coefficient based on the slot shape. And section 3.1.1 of your textbook gives you procedures for calculating Carter coefficients for different slot shapes. And the reason that you'd incorporate this in this stage of your analysis is just to give you a more accurate permanent magnet design or magnetizing winding design. So you don't actually need to do this. You could just assume that your Carter coefficient is 1 and then go through your design process. At the end of the process, you do your detailed analysis and you discover, oh, I've got less magnetic loading than I thought I dimensioned. So then you end up increasing your permanent magnet thickness a little bit to try to get yourself back up to the right amount of magnetic loading. Well, if you use the Carter coefficient, you can reduce the number of iterations you have to have on refining your design. So these are all the steps that I have for you. I want to make a final comment here on what the result of this gets you. The result of this can get you a template design that you can use for optimization. And you might say, well, why bother with a template design? If we're just going to parameterize our rotor and our stator anyway and let our algorithm search the design space, why would we come up with a template design? It turns out that this is actually a really important step of your design process. Your template design gives you a crude estimate of what you expect all the dimensions to look like. It doesn't provide a detailed analysis of all the dimensions, but it gives you a crude step. And this is important for refining how big of a design space you need to be searching. If you're trying to design a 1 megawatt motor, you're going to have a rough idea of what the radius, the length, the radius of your rotor, the axial length of the machine, what a rough approximation for your air gap length is, how big your teeth should be. And you can use that to impose constraints on your parameters in the design process. It's important to impose constraints, or otherwise you spend all your computation time evaluating designs that could not possibly be used as 1 megawatt designs. So it allows you to refine how much of the design space you actually need to search. It gives you an idea of approximately where your best design should reside. And the second thing that this does is it gives you an initial design that you can actually refine without an optimization algorithm to come up with your final design. And so what that might look like is you might take this initial design and you would then perform a detailed analysis, whether this is FEA or a magnetic equivalent circuit, to calculate the performance variables. And you calculate your performance variables, and then you decide whether it's good enough. If it's not good enough, you're going to tweak the dimensions of your design and perform another detailed analysis. When it is finally good enough, then you're done. You've got a design that you can build. So this is just a crude way that you can come up with your final design if you don't want to deal with all the overhead of doing a complete design optimization. That is, you use these analytic steps to roughly dimension your design, and then you analyze your design and you use your engineering knowledge to modify your dimensions so as to improve your design metrics. That is, your torque density, your torque ripple, your efficiency, and so on. So, in summary, this video has defined an analytic procedure to determine an initial design of an AC machine. We started from the very beginning where we defined a design specification, and then we talked through all of the decisions you have to make along your pathway to construct a complete set of dimensions. We talked about how you pick your magnetic loading, your electric loading, your rotor radius and length. We talked about how you select your air gap length. We then use this to talk about how we perform our winding design and come up with the total number of ampere turns that have to be within a coil. We then talked about how to calculate the back EMF of your machine and ways that you can change what your back EMF is to accommodate a constraint on your voltage, your terminal voltage. We've talked about how you dimension all of the various dimensions of your motor cross section, so your tooth width, your tooth depth, your magnet thickness, and so on. And finally, we introduced this idea of a correction factor for your effective air gap length for when you're dimensioning your magnets. And then we finally remarked about how this fits into the broader picture for designing your machine.